Hi, in this video, we're going to continue to talk about recursion in a little more depth. You might question is, okay, so recursive function is just a function calling itself and keep calling itself. How does it actually give us the ultimate answer? How does it actually work? So let's actually step through a concrete example of how it actually returns the answer that we were looking at. So we were looking for. So let's work out how sum of 3 works. Okay, so the first time we're here, sum of 3, n is assigned the value 3, right? 3 is not 0, so we don't come in here, we don't return. So what we come into is this line, right? So it would actually say return 3 plus 3 minus 1, which is 2. So this would return 3 plus sum of 2. Well, it can't quite return yet because we still have to evaluate sum of 2. So it would call sum n equal to 2. Okay, that's the recursive call here. And then we get into here, n is 2. 2 is 2 equal to 0. Well, no, that's false. So it does not come in here. So again, it will come to this line. And what we have here now is 2. N is 2. It will return 2 plus sum of 2 minus 1, which gives us a 1. Okay, and again, we cannot return yet because we have to calculate sum of 1. So we come into sum, and now n is 1. Okay, n is 1. And then 1 is 1 equal to 0. Well, that's also false. So again, we come to the last line. And this time is return n equal to 1 plus sum of n, which is 1, 1 minus 1, and we get a 0. So yet again, I think you might be getting bored now that we cannot return yet, right? We still have to calculate sum of 0. So we do sum of 0 one more time, or we do sum one more time with n equal to 0. And now 0 is equal to 0. So we're finally able to get into return 0 here. Okay, so we're finally hitting the trivial case that we talked about earlier. We no longer have to do recursive call. We can actually return a real number now. So remember how we got into here, okay? We got into here because in the previous case, when n minus 1, we're trying to calculate sum of n is 0. So now when this guy returned, this 0 gets returned to this place. Okay, so we replace the sum of 0 with 0. And again, we're at this line where we're returning, right? So we calculate 1 plus 0 here, which gives us a 1. And that 1 is returned to where this sum of 1 is called, which is back here, back here. So that 1 goes back up here. And again, we are back into the place where we can return 2 plus 1, and that gets returned to here. So 2 plus 1 is 3, and we're finally here, which is the kind of the, depends on how you look at it, the top most call to sum, and sum of n equal to 3. So we're finally able to return a real number. 3 plus 3 is 6. And we return 6 to whoever calls sum of 3. So I hope that you see how the recursive version works. Now, one thing to kind of note that the thing that we just went through, let me go back here. So this is the beginning, and then we do, sum of 3, sum of 2, sum of 1, sum of 0, and then so it grows, and then now we go back, because we're returning now, we go back. So what did that look like to you? That when the recursive function, right, it's called multiple times and then it returns multiple times. That operation, it should kind of resemble a data structure that we've talked about very recently, right? You remember what that data structure is called? Well, that is really a stack. Okay, so specifically, this is a call stack or a function invocation stack. So every time you call a function, that call actually pushes the function's record, or in another word, the functions, anything that's associated with the function, right? It's parameters, it's local variables and stuff. So anytime you call a function, it pushes the function's record onto the call stack, and then when you return from the function, it pops its record off the call stack. So recursion really relies very heavily on using a stack to do its job. All right, hopefully that makes sense. Now, one other kind of business we would like to take care of is that, well, so sum of n, it works for a positive n, or even 0. What if n is negative? Then the way we want to do this is that if n is negative, then we actually should, instead of starting at positive 1, we start at negative and then decrease until we get to whatever the negative n is. Now, if we just use our current problem, the current implementation to solve this, what are we going to get? So think for a moment, what's going to happen? And if you want, you can also try to run the code and see what happens. So I'll show you what happened. So let's do print sum of -5, something like that, okay? And when you run it, well, it complains. And it's a pretty nasty complaint too. It says the maximum recursion depth exceeded. That kind of makes sense if you think about it, because if I say n minus 5, what happened is the recursive case is going to do n minus 1, and that's going to be -6. And then the next recursive call is -7, -8, -9, so on and so forth. It keeps getting smaller, right? And if it's actually going away from 0, so it will never reach 0. So in a way, it actually will do it does an infinite recursion. I use the word loop here. It's not quite right. It's an infinite recursion. Okay, it will recurse. I'm going to fix it right here. Forgive me for a moment if this thing works. It'll recurse infinitely. Okay. So how do we fix that problem? Wow. Okay. How do we fix it? So pause, think about for a moment. How do we fix it? Okay. The way to fix it is based on the following observation. So let's look at an example. Let's do sum of -3. Sum of -3 equals -1 plus -2 plus -3. You can actually factor out the negative number here. If you remember your, what is this, algebra? So this is the same as the negative of 1 plus 2 plus 3. 1 plus 2 plus 3 is really the sum of 3, right? So what we've come to is that sum of -3 is equal to the negative sum of 3. Or in other words, sum of n equal to the negative sum of -n when n is negative. So what does that mean in our actual Python code? Well, we can just say if n is less, if it's negative, also is less than 0, so we just return negative sum of -n. And that's that. Let's hope that it works. I'm going to put a 3 here just to make sure we know it should return -6, right? So, and there we are. So, and if we say -100, it should give us -50, 50. All right, here we go. So that's kind of, that's the answer in case of a -n. Okay, so I think I've kind of at least introduced the basics of what a recursive function is. Then here is, I'm going to ask you to write or to calculate the factorial of a number. This is a very classic example of recursion. So what a factorial is, if you remember, is that the n factorial is basically n multiplied by n minus 1 multiplied by n minus 2 all the way to 1. Okay, so for example, 5 factorial is 5 times 4 times 3 times 2 times 1. And if you want to see, if you actually want to let's say define this in terms of recursion, it's and if we look at this example in particular, right? So 5 times all the way to 1 is equal to 5 times, but the 4 multiplied 4 times 3 times 2 times 1, we do that first. And what does this look like to you? This is just 4 factorial. So 5 factorial really equals to 5 times 4 factorial. And if you generalize this, it really means n factorial is n times n minus 1 factorial. All right. And the base case or the most trivial factorial is when n is 0. 0 factorial is defined mathematically to be 1. So pause the video for a moment and try to write a recursive factorial function. Okay, so I hope you've done it, but I'm actually just going to write it here. How about we do that? I'm going to define factorial of n. So as we said, what is the most trivial factorial? If n is 0, we return 1. Otherwise, we just return n multiplied by factorial of n minus 1. So let's test this. Test. Factorial of, let's say, I don't know, 3. That's 3 times 2 times 1. Well, that's also 6. Let's try 4. Okay, so 4 times 3 times 2 times 1, that should be, yeah, 4 times 6 is 24. So let's hope we got it right. So there, it's 24. Okay. Now, I just want to point out, I haven't introduced the formal terminology is, but we kind of said this many times. This is really the recursive case, whereas 0 factorial is the base case, right? And yeah, we can generally identify very easily in a recursive function what the base case is and what the recursive case is. So after looking at these two examples, here's a summary, and I hope you can recognize this, that there are, to any recursive function, 3 very essential ingredients or components. Okay, so the first one is what's called the base case, or the terminal case, or there might be other names for it. Basically, the base case is where the solution is so trivial that we don't need to make recursive call to get the solution. Right? Again, the base case is where things is so trivial we know the answer right away. And then in the case of sum of n, the base case again is when n is 0, we know the sum of 0 is 0. Right? That's the base case. That's the most trivial case. And then there is the recursive case. Right? So recursive case is about calling the function itself. And calling the function itself, and it should give the recursive call an easier or simpler version of the problem. And the goal, again, is to ensure that it will eventually reach the base case and stops. Okay, so if it's not an easier or simpler problem, what might happen? As we saw, if it's not an easier problem, if it doesn't bring us closer to the base case, then your recursive call is going to become infinite recursive calls, and it will never terminate, and that's not good, right? So make sure in your recursive call it's always something easier, something a little simpler. The final component is that once you have the result of the recursive call, how does that help us to solve the current problem at hand? Right? There's a way to use the result from the recursive call in combination with something else, in this case, just the n, and together this gives us the solution to the current or the original problem. Okay, so those are the 3 essential components of pretty much any recursive function.